Hello friends, myself Soumya, Assistant Professor, Department of Mathematics, Government Corporate College, Tipton. So continuation of the previous session. In this session, we shall deal with the theorems on similarity of sets, the standard theorems on similarity of sets, theorems on countable sets, and the theorems on uncountable sets. So the first theorem proved that the union of two finite set is a finite set. Union of two finite set is a finite set is the statement of the theorem. We shall see the proof. So two sets, here we shall consider the set A and set B. Let those two sets be empty sets. If the two sets A and B are empty sets, A equal to B equal to 5 empty sets, then A union B is also 5, which is empty set. So empty set is always a finite set. Therefore, if A and B are two empty sets, then the union of a two empty set is also an empty set. So we can say that the union of two finite set is a finite. And coming to the second case, if the two sets A and B, A and B, A is equal to B or B is equal to A, means number of elements in the set A is equal to number of elements in the set B, then A union B equal to A or A union B equal to B. With these four conditions, we can say that A union B is finite. So here we are defining the four conditions, that is A equal to B or B equal to A, which means the number of elements in the set A is equal to the number of elements in the set B, or if A union B equal to the set A or A union B equal to the set B in these four cases also, because A and B are finite sets, therefore A union B equal to A or A union B equal to B, which makes A union B a finite set. And in the third case, if A is a non-empty set and B is a non-empty set. In first two cases we have considered A and B as an empty set, and in the second case we have considered A is equal to B or B is equal to A. In the third case we shall consider A and B both are the non-empty set, and given A and B are the finite sets, then we need to prove that A union B is also finite. For that we shall consider a natural numbers n and m, then there exist the number of elements in the set A as small letter n number of natural numbers, and B as the number of elements as small letter m of the natural numbers. So that implies if A intersection B is equal to empty set, then A union B has m plus n elements. Therefore, A union B will be having together of n plus m number of natural numbers. So, if A intersection B is a empty set, then in the union of the two sets will be having m plus n number of elements, which can be denoted as A union B is having n plus m number of natural numbers. Therefore, because small letter n is finite and small letter m is finite, the number of elements n plus m is also a finite number. Therefore, we can say that A union B is finite. Then suppose if A intersection B is not an empty set. A intersection B is not an empty set, it is a non-empty set, then there exists an element K containing A intersection B which has K number of natural numbers. A intersection B will be having a K number of natural numbers, then A union B will be having n plus m minus K elements, because A intersection B is a non-empty set and it contains K number of elements. The set A has m number of elements and the set B has n number of elements. So, the union A union B will be having n plus m and the common elements k number minus k elements, because n is finite, m is finite and k is finite. Therefore, A union B will be having finite number of elements of natural numbers, that is n plus m minus k. Therefore, we can say that A union B is finite. So, in all the cases, A union B will be finite. Therefore, if A is finite and B is finite, then we can say that A union B is a finite set, which is the proof of the given. Let A be a countable set, then either A is finite or denumerable, because we know the definition of a countable set. So, if A is a countable set, then either A will be either finite or denumerable. So, in the first case we should take A is a finite set. So, because A is a finite set, every subset of a finite set is always a finite set. Therefore, every subset of A is finite and hence countable. That is the first case. In the second case, when A is denumerable means A is equal to the set of natural numbers n. Denumerable definition: A is equal to the set of natural numbers n. Let us consider the set A equal to the elements a1, a2, a3, etc. and let B be the subset of A. We have to prove that B is a countable set. Here we have considered A as a countable set. B, a subset of A, we have to prove that it is also a countable set. So, if B is finite, then B is also a countable set, because A is a countable set. A is either finite or countable. Therefore, we consider the subset B of A. B will be either finite or infinite. If it is finite, then we can say that B is a countable set. Suppose if B is infinite, let n1 be the least positive integer. Such that an1 belongs to B. Since B is infinite, B is not equal to the set an1. And let n2 be the least positive integer, such that n2 is greater than n1 and an2 belongs to the set B. Therefore, B is not equal to an1, the set an1, an2. Continuing like this, we will get the set B is not equal to an1, an2, etc. So, we shall define the function f from n to B by f of k is equal to a n k for all k belongs to n. Then f is 1, 1 and on to, because B is equivalent to the set of natural numbers. Therefore, which makes the set B as a denumerable and B will be a countable set. So, by the above 3-4 lines, we can define the function f from n to B by f of k is equal to a n k, which makes the function f a 1, 1 and on to. Because the function is 1, 1 and on to, we can say that the infinite set B, if the B is infinite, the infinite set B is equivalent to the set of natural numbers, which makes the infinite set B as denumerable and hence it is a countable set, which is the proof of the theorem. So, for this you can take a test, or you can write the definitions like define the cardinality of set and define the finite and infinite set, and also the descriptive questions you can try at home. So, prove that if A and B are finite sets, then A intersection B is also a finite set, and this is the reference. Thank you.